right, the auxiliary questions. What is the impulse on A? Well, what's the formula for impulse? Again, there's two formulas for it. You got F dt. Again, sticking the dot in there, I have it. F dt, and also the change in momentum. Which one do you use? Sometimes people ask, and that's whatever you're given. In this case, change in momentum is the 0, 1. All right, so change in momentum of A would be PA final minus PA initial, which is, let's see, 10/7 times 3. I guess I changed my notation to, that should be a 3. Uh, 30/7. 4 2/7 minus my initial, which was 18. So that's about 4.28 minus 18, negative 13.72.
It's a 714.
All right, what's the impulse on the 4 kilogram mass? So that would be P4 final minus P4 initial, which is, well, initial is -8, so minus -8. And my initial would be 47. So that's 47 plus 56/7, which is 96/7, which is 13 point. And this is as expected, that the impulse on A is the opposite to the impulse on B. This is Newton's third law, or implication of Newton's third law. So therefore, in total initial impulse plus the total final impulse should be 0. Because whatever one gains, the other one loses. That's conservation. Questions to hear? All right, one other thing I want to look at here is the kinetic energy. My initial kinetic energy of the 3 kilogram mass, you know the formula, you should be able to scream it in your sleep. 1/2 times 3 times 6 squared. Units. and this is 8 joules. So my total kinetic energy beforehand, K initial. What is my total before?
54.
Not 64.
Oh, that's a 50.
What?
54
Total.
total. Oh.
Total. There's a calculator dependence that I'm sensing here.
46.
How'd you get 46?
62.
62. Yeah, these are positive, both positive numbers. All right, so 62 joules. My final momentum, or sorry, final kinetic energy, K final, I'm gonna treat them as one object. So 1/2 times 7 times 10/7 squared. Should we 2 point? No. 17-ish, 16-ish.
I got 57s or 7.14.
Good, 57.
57s or 7.14. No, I got 57s as in a fraction or 7.14.
Ah, got it. Oh, yeah. Units. All right, so we start out with 62 joules of energy. We end up with 7.14 joules of energy. So by change in kinetic energy, 7.14 minus 62, negative 54.86 joules. Obviously, we lost some kinetic energy here. We lost energy. Why is energy not conserved? Or why does it not seem to be conserved? When these two things collide, what force is involved?
Normal.
Okay, is that a conservative force or a non-conservative force? If you don't know, you got a 50-50 shot.
I guess non-conservative.
It is indeed non-conservative. Gravitational force and elastic force are the only two that we've touched on, which are conservative. So there's a non-conservative force, but energy has to go somewhere. So what happens when these two things collide into each other? We lose this macroscopic energy. Where does that energy go? Because energy actually is conserved, it has to go somewhere. How does it manifest itself in this problem? Or in a reality?
Well, usually if it disappears, it's usually like heat or something.
Yeah. The two objects probably are warmer on the surface. It goes from being the macroscopic kinetic energy into internal kinetic energy. And the internal kinetic energy is directly related to temperature. So it'll heat up. The textbook likes to use this thermal energy as a catch-all. Fine, just recognize that thermal energy is just kinetic energy, just within the object. All right, questions before we make it look more complicated? I guess I should wait to see if someone has a question before I raise this time.
No questions.
All right. So I got my 3 kilogram object cruising along to the right at 6 meters per second, and then I've got a 4 kilogram object cruising to the left at 2 meters per second. And, this is before. Afterwards, the 3 kilogram object's cruising to the left at 4 meters per second. The 4 kilogram object what is the final velocity of the 4 kilogram object? They are going to collide. Just put in collision. They will collide. If there's a collision, what's the first thing that should pop into your head?
Conservation of momentum.
That's the thing. So if you're ever in a car accident, conservation of momentum. And then, is everyone all right? I know what the total momentum beforehand is, because we've already done that. Again, we will say to the right is positive, and we end up with 10 Newton seconds. What's the final momentum? Keeping in the spirit of what the previous answer to the previous question was,
Which should be the same.
it should be the same. Conservation momentum. All right. So, what is the momentum of this after the collision?
12 Newton seconds. 12 Newton seconds.
No. So P3 final.
Oh,
Yep. Did you realize it was a mistake?
somewhat, and going back, starting the process.
It's simple. You made a very small mistake. Of crucial, but small. Yes. Negative. So negative 12 Newton seconds. And so P4 final. Well, I know my total is 10. One of the numbers is negative 12, so negative 12 plus what gets me 10?
18.
Try that one again.
22.
So I know what the final momentum of the 4 kilogram mass is 22 Newton seconds, and that's going to be equal to 4 times V final, V4 final. Mass times velocity. And so my final velocity of the 4 kilogram mass is 5.5 meters per second. Now let's take a look at the kinetic energy. All right, so my initial kinetic energy hasn't changed. That's still 62 joules. My final kinetic energy has got to be, well, we just add up the individual ones. So 1/2 times 3 times, is it 4? 4 squared. Plus 1/2 times 4 times 5.5 squared. So what do we end up with as our final kinetic energy?
Should be 84.5 joules.
All right. So we gain kinetic energy in this. We smash these two things together and we get more energy out than we started with. There's a word for this. So change in kinetic energy was greater than 0. Most textbooks will call it impossible. I call it Flubberesque. I'm assuming that you're familiar with Flubber or The Absent-Minded Professor. I'm getting blank looks here. Flubber was a movie starring Robin Williams. The Absent-Minded Professor, the original, starred Fred MacMurray, and there was another version of it that had Harry Anderson as the lead. It's a material that, as you bounce it, it gets faster. It'll bounce higher than its initial height. If you just drop it, boom, and then it just gets going faster and faster. And that's, in essence, a free source of energy. It was, as would be science fiction. If you haven't seen any of the Flubber movies, I recommend you. Personally, I like The Absent-Minded Professor, but I'm also of somewhere between your parents and your grandparents' generation. All right, so obviously I bring in kinetic energy into this because there's some connection here, and so let's take a look in general here. So for the collision, we'll have momentum conserved. So the initial momentum equals the total final momentum. And then what happens with the kinetic energy? Well, if the change in kinetic energy is less than 0, and they stick together, naming convention number 1, perfectly inelastic. Naming convention number 1. Naming convention number 2, inelastic. If the change in kinetic energy is less than 0 but don't stick, in the naming convention number 1, oh, that should be a 2 there. Naming convention number 1, this is known as inelastic. Naming convention number 2, this is known as elastic. You can see where there might be some confusion depending upon which textbook you're using. If the change in kinetic energy equals 0, convention number 1, this is known as elastic. Convention number 2, this is perfectly elastic. And changing kinetic energy is greater than 0. And this assumes that there's no explosion or any additional source of energy. They would just call it impossible. Now, for whatever reason, it's like the names of clouds. You know, I can learn it in short term, but long term doesn't hold. So, Fox convention. Because I think it avoids the overall confusion. Perfectly inelastic and perfectly elastic. So if they stick together, perfectly inelastic. If kinetic energy is conserved, in addition to momentum being conserved, I do perfectly elastic. Impossible, as we just introduced, this is what I refer to as Flubberesque. And that leaves the gap right here of what, obviously, if I use inelastic or elastic, I deal with possible confusion there. And a couple years ago, students did suggest a word that I liked, imperfect. So those are the imperfect ones. On tests, master sets, and so forth, this is the naming convention I'm using. I was grading some 110 master sets and asked what type of collision given this right here, or sorry, given this right here. And a lot of them refer to the collision as inelastic, which forces me to have to figure out what is the textbook using? Or the person, if they're getting a tutor, which convention were they using? So don't make me have to look it up in the textbook, what the textbook does. Now we have an advantage with this. If we have a perfectly elastic collision, let's say these two right here have a perfectly elastic collision. I don't have to tell you any information about afterwards other than the fact it's a perfectly elastic collision. What are the final velocities, plural? In other words, what is V3 final and V4 final? We have two unknowns, so how many equations do we need? One of them, conservation of momentum, and because this is perfectly elastic, the other one, conservation of kinetic energy. So I have 62 equals 3, and I'm gonna say afterwards, I'm gonna let this be C and that be D. So 3C plus 4D. And then for kinetic energy, oh, that wasn't 62, that was 10. Sorry, 10. For that, this is the momentum, P initial equals P final. And then K initial equals K final. That's gonna give us 62 is equal to 1/2 times 3 times C squared plus 1/2 times 4 times D squared. Two equations, two unknowns. First off, questions about where these equations come from.